concept to prototype. How do you pick an idea, all right, and develop it through the process to realize it? All right, so my name is Douglas Aite, and I run an inspiring organization called The Maker's Place, and we support K-12 to university students bridge their skills gap, because most people at the university level, sometimes they complete school without practical skills and becomes a challenge. So what we are doing is to inspire skill, innovation, creativity, problem solving at the basic school before they go to the university or they come to the university. What else we do is we provide internship opportunities. So we've had a lot of students from ACity take internship at Maker's Place, University of Ghana, UCC, different students from different places take internship, others take national service at our end, and then they build from there. I'm working with different schools on different capstone projects. So one of the capstone projects I'm currently working on is with Arizona State University. So we're doing two important projects. But before I come back to this, I'll be working with Northeastern University, right from University of Ghana, where we work on capstone projects, because that's something that I love to do. So it's a combination of having students in the US work on the same project and students in Ghana work on the same project, and then we look at how they look at the design from different perspectives, right? And we started with neonatal incubator with Northeastern University students. We were able to do it successfully. If you check on LinkedIn, you'll see that. Now, we've moved on to, now I'm working with WPI, also on another project that is also completed. And recently, I have two important projects I'm working on with students from Arizona State University. That is the Byte Box. That's what you see. The project aims to engage students in rural Ghana with STEM subject through robotics kits, right? So we're working, that's Maker's Place, as I told you, we work with schools and students and teachers trying to understand which best approach should STEM be taught in the schools. And you know, robotics hardware is very expensive, right? So if you're talking about STEM education, and the hardware is very expensive, then it's only those who are privileged will have access to that. So why don't you build a low-cost robotics kit that will allow students, irrespective of their background, to be able to appreciate and learn robotics at the basic level. So we have students from Arizona State University. Every year, it's more like a capstone project. So wherever they get to, if they move on, another student enrolls and then they take the project up. So we are in the second phase of this particular project. And then the neonatal incubator for rural Ghana, that's also another project. I'm looking for students to collaborate with the students in Arizona State University, because they've already formed the team, they've started working on it. We have the third cohort, so I can get another group of students, and then they also build from Ghana, and then they compare. I don't know the opportunity you get out of it, but it is your call if you want and you are interested in that. Today, you can find more about what Maker's Place is and all of that. Today, I'm more interested in rapid prototyping. All right, rapid prototyping. Sorry. So I said from idea to prototype. Sometimes final year students, they say, build a project. We want you to design something. You should be innovative. You should be creative. This project has been done before. We don't like this one. Change it. Then you become confused. You have never tried it, but they said you should be innovative, you should be creative. How do you get to that level? It means that somebody has to walk you through the journey, right? Because a lot of people have never tried anything and failed before. They've never broken a gadget before. right? They've never tried even opening their own phone to see what is wrong with my phone, what is inside the phone that is making this work. I quite remember at University of Ghana, there was a student who had said, my laptop is spoiled. I said, fix it yourself. He said, how am I going to fix it? To get spoiled. I said, the thing is not working already. Take the screwdriver, open it, and let's see what is happening, right? Eventually, she was able to do it, okay? And if she had taken it serious, maybe she would be servicing laptops for other people in the halls and be making extra money, right? So right now, what I'm looking out for is that we are looking at this particular workshop from theoretical framework, right? So it's a guide. Let's say I'll give you a scenario, and then we'll do the brainstorming together, and then we'll find the solution around it, right? So there are different framework. So what we need to do is, one, this workshop emphasizes thinking before making, which is very, very important. Thinking before making. Because if you don't do that one right, you end up losing a lot of resources. Because you do try and error, it doesn't work. You do try and error, it doesn't work. Because there's no guiding principle that you are following, right? So we must make sure that we do it that way. So identify real human or community needs. So I'll give you scenarios around that, and then we'll see how we can go around it. Then structuring system concept. So this time we are looking at IPO, right? The IPO model, input, process, and output. Everything around that is like that. Everything around us, every system has input, process, and output. So how do you envisage that? How do you understand that? Your understanding of this helps you to look at the problem and then devise a strategy. So it becomes easy for you to even draw your block diagram if you understand it that way. It becomes so easy for you to, if you are looking at software consideration, to be able to draw your flow chart, right? So we'll look at the IPO model as well. Then we'll do evaluation, because when you are done, you need to evaluate what is the feasibility, what is usability, what are the ethics around what you are designing. If you are designing medical device, what do you need to know about ethics, right? You can pause, ask question. I want it to be more interactive. So this is the structure I'm looking at. I'm looking at explain. One, at the end of this class, clear learning objectives. You should be able to explain the flow from problem discovery to prototype, right? Prototype delivery using step-by-step reasoning process. Two, you should be able to understand the conceptual model of the IPO, right? Input process. And then you should be able to apply design thinking and basic engineering principles to healthcare or community challenge. So I have two challenges. We'll look at how we will solve it. Then we'll do an evaluation and then reflection. Core concepts. Design thinking loop. So I know some of you have done some bit of design thinking, or you know about it already. Then we'll look at the engineering logic, right? Framing systems with clear input processes and then output. Then we'll look at the conceptual modeling tools, right? So if you want to model the concept, what tools are available at your prototype state, right? If you get to, there's a workshop where I ran and I said, how do you marry computational thinking and then design thinking? How do you put them together? The nexus of computational thinking and design thinking. When do you bridge them to be able to realize a project? I think that's something we can look at later. Then we look at the human-centered focus, usability, accessibility, and then ethical implications. All right, who can help me read this, and then we solve it as a team. So this is your problem. How do we solve this? Every morning, hundreds of students arrive at Bright Future Academy, a large public school in Accra. Since the pandemic, the school's health policy requires that students showing signs of fever or illness be identified before entering the classroom. So there's an issue, all right? Now, but here's the challenge. The school has only one nurse and then automated equipment. Students queue for long periods just to have their temperature checked. Okay? On a busy days, Many students skip screening altogether, and then teachers complain that classes start late. Then the nurse often overwhelmed with the number of students that comes in. Parents are concerned about possible infection spread among the children. Your role is to design a concept for contactless screening system that could help detect unwell students efficiently without physical contact or expensive hospital-graded equipment. This is the concept. This is your problem, right? Now, how do you go about it? Yes. From idea to product, or from concept to prototype. How do we get there? Yes. This is the challenge. You are biomedical engineers. You are electrical, electronics engineers. How do you find a solution to this? First of all, is it relevant? Right. Yes. So what do you do? Yes. Let's have an interaction session. Yes. This is the problem we are facing. You are a design engineer. Help us solve this. Yes. What do you do? Yes. Yes.
So, with signs of fever, meaning that we need to measure temperature.
We need to measure temperature, yes. So she says we need to measure temperature, right? Because of the signs of fever. Okay, yes, continue.
And because we need it as contactless, perhaps we can get some sensors, ultrasonic sensors, or employ some sensors that at a distance they can be able to detect the presence of the person and be able to also give a reading.
Okay. Yes, who else? Yes. Yes. So you have a problem, right? You are design engineers. Design engineers, strong electronics background, strong programming background, appreciable knowledge of microcontrollers. Now, this is the problem a school is facing. How do you solve it? Yes. Okay.
Something that they should not have to contact before we get anyone on this. You can basically use, let's say, infrared sensor.
Infrared sensor?
So let's say we don't also want classrooms to be. So each classroom will have a design, such design there. So if the students come, they will just carry their temperature, and then if your temperature is
You are solving the problem. You just want to solve the problem. You are not there yet. Think through the design thinking process. You've not. When you come to the prototyping stage, that's when you are thinking about what to do, right? What hardware and other things to do, right? Now, what is the purpose? Who can tell us in 60 seconds or 30 seconds what the problem is? Yes. So the key word is what? Reduce. Right? So the concept should be morning health check, right? Contactless school screening. But the purpose is to reduce the queue. And then, what else? And nurse overload. These are the key things. So, in your design, that should be your guiding principle. How do you reduce the queue? How do you reduce the load on the nurses? Do you get it? Okay? So, as an engineer, where do you take it from? Now, you know what? we know why. Okay? So you want to reduce the queue, and then you need to reduce the load on the nurse. So what do you do from here? Yes. Sure, sure. Yeah. Yeah, but you have a bit of idea around it, but think about it this way. You already have the problem scenario, and then you have the problem statement, right? So the next phase will be to do more of what we call brainstorming, right? Now, the objective should be clear. At the end of the day, you want to reduce the queue and you want to reduce the load, the overload, right? So you want people to just go there, measure temperature, go how you want to measure it. This same problem can be applied to an OPD where you go there and you queue for a longer time just to go, and the doctor says, oh, you need a rest. This is stress. Go home and take some water and sleep. And then you say, just this, and I've been in a queue for 2-3 hours. Can you imagine that? Right? So what if you can take your vitals from the house, transfer the data to the hospital before you even get there? Right? So it's not just for this, but it can be repurposed for other things as well. So all computer systems takes data into a system using what? Input, right? Carry out the processes on the input and then display the results of the processes using the output, right? So using the IPO model, which is your input, your process, and your output. So what will be your input? If you want to reduce the load, what will be your input? What goes into your input? You should think about that, right? When it comes to the processes, what will go into your processes? And what results do you want to see? Which will be your output, right? So in your input, these are some of the things you need to look at. Temperature signals, right? The keyword is that it's non-contact, right? So if it's non-contact, then you need to use what? IR, okay? So you use the IR sensor and then you point it on the forehead and then you check the temperature at the entry level. Then self-report kiosk, that's something that you want. Maybe you have that one, somebody goes there, then it scans them, and then they move. You are looking at different scenarios of addressing the challenge where you are reducing human interference, right? So it's more like a self-service. Okay. Now, there's a bit of manual there which you want to also do away, depending on how you are looking at the input parameters. Because your input parameters will inform you on what to do next, right? Then in your process, there should be a precondition. So if it's a temperature monitor, then you must have some basic information, a predefined data, and then you compare it with it, what you are designing, right? So the average temperature should be what? So what temperature is acceptable to be normal, and what is not acceptable, right? So you need to have that pre-data first before you go into it, so that when you are getting your output data and then you use that particular data to compare, is it right? Is my design effective? And all of that, right? So in your process, you are saying that your pre-screening logic, right? So this is where you build your logic. It says that if the temperature is greater or equal to 37.8, you flag red, right? Then if the temperature is 37.4 to 37.7 degrees, all right, you say yes, the amber, all right, else you admit. So if the temperature is not within this, any of this scenario, then you admit. It means the person is okay to enter, right? Then you take two readings 10 to 15 seconds apart, and so that you reduce false positives, right? Sometimes, medical devices, people are diagnosed wrongly. People are diagnosed wrongly, and then they give them wrong medication, and it leads to death and other things, other complications. How do we address that? Okay, because sometimes the temperature sensor monitor at the hospital, the thermometer, is the thermometer they've been using for the past 6 months, 1 year. So, thinking that it is correct, sometimes there's a drift. These are electronics components. They can, based on how they handle it, they will have effect on the reading. But who is checking to make sure that that data that you are acquiring is the right one? So that's a bit of a challenge for biomedical engineers. All right, we'll end here, and then afterwards we'll continue. So sorry. Yes, welcome back. So for the recap, we started looking at a problem scenario. So from the problem scenario, we trying to deduce the best approach in addressing or solving the problem, right? In practice, what people do is that they go straight into the prototyping state, right? Oh, they have an idea. Someone has the arm amputated. How do we solve it? So, let's build a prosthetic arm. How do we build it? Then they go, let's do a sketch and let's design the arm and then 3D print it, right? Or mold it or whatever they want to do. So they go straight into the actual prototype state without going through the design phase, right? Which is the design thinking phase. Now, system thinking in your design. Because if there's a challenge with your output, right, you need to go back to the base, your baseline, all right? So if the system thinking bit is missing, right, then you yourself, you get confused because which parameters are you comparing it with, right? So what we started from the first phase was more focused on the system thinking phase, right? So we looked at the process. We talked about the inputs. So if you want us to do a recap, so we talked about the input. Based on the scenario, we are reducing the number of people that are going there at a time, and then we are also reducing the burden on the nurse, right? So we said that we need a temperature signal, but the temperature signal should be non-contact. The one we already have, it means that they put the thermometer to measure the temperature. We are not doing that, right? So we are looking at non-contact. Then, after we looked at that, then we come to the process, right? If you compare this, we'll go to that, but if you compare it with normal, straightforward design, this process will more be on your flow chart, right? You need to have a flow chart. If the temperature is this, what do you do? If the condition is this, what do you do? And all of that. But this approach requires no hardware, but it's more like realizing the full solution right in front of you, right? So we look at the pre-screening logic, right? So at the entrance, what do you want to do? So you want to check if the temperature with the parameter. So if the temperature is above this threshold, you want to flag red. And then if the temperature is in between this threshold, then you said, yes, there is a symptom, and therefore you want to call for review. And then if the temperature is not within this, okay, then you admit. That means anyone whose temperature is not within this have straight access, right? Then the amber is not that serious, right? So that one, the nurse can review you, maybe tell you to wash your hand or something. But if it's red, then it means that you need to wait, okay? But you also want to say that, okay, 100 people access the place in a day. 20 people went through without any further screening, all right? Out of the 80 left, maybe 60 also had issues but was not severe, right? And then the remaining 20 had more issues, therefore they were referred or something, right? So you want to have a data log in your design as well. So in your output, you are saying that if at the gate, right, the moment the light is green, you will have access. Okay? The moment the light is green, you will have access. But if the light is red or amber, right? If the light is amber or red, then you need to see the nurse. So that's where you do more of human-to-human interference, right? Then you also need to have a dashboard, okay? You need to have a dashboard that is giving you the average, the number of people that are accessing that. So you must have some database behind the scenes that will be collecting that, and then you have your CSV file at the end of the day, and then you can use that one for your data analysis, right? Then after you've gone through the pre-screening logic, now you want to look at it from your simple logic table, right? So what is the condition? What action do you want to take? And then what will be the destination, right? So we are saying that in your logic table, which you can call your flowchart, right? So if the temperature is between this 37.8 degrees, then it says that you flag red, then what do? You notify the nurse, right? Then if the temperature is between 37.4 to 37.7, right, then you assume that there's a symptom. Therefore, you also flag the amber. And then sometimes you are saying that if it's amber, then maybe they should wash their hand and sanitize and wash it, and then they can move quickly. But if it's green, then there's no case, there's no trace, so the person will have to go through it, right? Then you also want to look at device error, all right? Sometimes you have your praise scope, maybe 3 scope, but there's values that are beyond that, right? What do you do? Okay, so you need to think about that within your design. Okay, so if you are seeing abnormal values, what do you do? Now, so this is the flow at a glance, right? Arrival, how do you go through it, right? So if you are speaking to, let's say, an investor or whoever is interested in your project, they may not be interested in that technicalities, right? Right at the entrance, what should be the process, right? So when you arrive at the entrance, you do the IR check. If that's the traffic light status, right? So you are using the traffic light to just explain how that process is. So if it is green, then you go to class. If it's amber, you stay in the lane, go to the review lane, right? And then the next will have to confirm, right? And then you override that particular state of rechecking, and then you go back, right? And then there's a counter that will count the number of people, either those who are overriding the system or those who are having access to the system directly. If you have questions, you can ask. Is the system thinking okay with you, the approach? Okay. Then you want to also look at safety, because having an MVP does not mean that you are ready to go for clinical trials, right? You need to, it goes beyond that. You need to have approval before you can even do your clinical trials. You cannot say that, oh, I have an MVP, therefore I'm going to try it on someone. No, you need to get the FDA involved. You need to know the ISO number you need to apply and all of that, right? So you need to also think about it from this perspective. Privacy. Okay, this is temperature, but you don't want to also tell people, you don't want, okay, this person came in the morning, he's having high temperature, so you want to keep their name. What do you want to do with their name? Do you have consent to be able to keep their name? What if, do you have a system that is protecting against vulnerability so that if there's a breach in your system, what will happen to the data? Who is going to have access to the information? And what are they going to do with it, right? You are seeing it from normal temperature, but what if it's other diseases, right? You don't want to get into that, right? And then you look at the dignity, the equity, then the force activity, the infection control. Now, here is your minimal viable pilot, right? This time, you want to, people in some certain workshop, what you do is that you get them some glue gun, glue stick, you get them some LED, some breadboard, and then they do a simple rapid prototype just to prove the concept of how this thing is being done, right? But this is the design thinking approach without necessarily have to do the core hands-on design. And then you do what you call reflection in your approach, right? Does the process shorten the queue whilst keeping the screening credible? What messaging keeps it non-stigmatizing, right? And then what breaks if the device fails or it rains? So maybe depending on where you are going to place it, you should also be thinking about that. What will the weather do? Is it going to be outside? All right, if it rains, what will happen? How would you build your enclosure? Would it be water resistance? You should be thinking about all of this in your system thinking. Okay, you just don't want to design a system like this, and then you are not thinking about how it will be used, right? You should, in your design thinking, you should be considering everything. How will your enclosure be like? Because you don't determine where the person should use it or how they should use it, right? If I purchase this and I decide to do an experiment outside, what will be the effect on the sunlight on the device if it's open? Do you get it? Now, if maybe I'm acquiring some data outside and then I left it and then it starts raining, what will happen? Okay, so you as a design person, through your design, looking at it from system thinking perspective, you should be looking at it holistically, right? So you say, okay, then I need to build an enclosure. It should be water resistance and all of that, right? Now, if it's fully enclosed, humidity can also affect it, right? How are you going to deal with it? So sometimes you open some circuit and then you see that there's some water, it has led to corrosion, and the board is not working. How are you addressing that? What material are you going to use? Material engineering, right? So even just your enclosure, there's a lot you need to think about. So you see that there's more work in the thinking than the actual prototyping. The prototyping is labor. Hey, hello. Prototyping is labor. You can give it to anybody to do it for you. Imagine if you have your circuit built, right? You can hire somebody and say that, I want you to, let me teach you how to do the soldering so that you just be placing the component on the board for me. That one is labor, right? But the actual work is in the design. The thinking side, it's your job, right? But the labor, you can outsource it. Hello? The labor, you can outsource it. Okay? Because the extra pieces is the labor, placing the components, and that's why nowadays if you go online and you send your Giba files and you want to put it, that they ask you, do you want it push it like they install the component and everything on it for you? Because that one is labor. If you say no, then you need to buy the component. Then when it comes, you need to sit down and be doing the soldering yourself. That's waste of your time. So why don't you outsource the labor? But the thinking, the flow, and everything has to be done by the engineer. And that is where the actual work is. So in other places, people argue, the engineers and technicians, who among them should be paid more, right? You know that, right? But they don't know that the engineer has to think more than the technician. The technician is only, is part of the labor process. All right. Any question on that part? So from end to end, these are the 7 steps in your system thinking. I'm done with that. If you have any question, we can look at it. Then I can give you one of the scenarios, and then I'll see how you address it. Okay? Any question? So what is the first approach? So the first approach is the purpose. So when you have the problem scenario, you must understand the purpose. Now, after you understand the purpose, then you look at your IPO model, right? Your input, your process, and your output. After you get that one correct, then you come to your simple rule, right? So you come out with a logic table. Then you look at the flow at a glance, and then you look at your safety, ethics, and usability. Then you look at your MVP, and your last one will be your reflection, right? So this is the system thinking approach in getting this thing done. The second phase of this, which I'm going to give you activity to do, the second phase is to walk you through one project, and then we walk through the whole process, right? That one is what normally people do, where they go straight from the project, and then they go to the block diagram, they go to the flow chart, they go to the wiring, and then they do the testing, and then they do the review, right? We are not going to do that one right now, but I'm giving you another scenario. If you can put yourself into a group, then you can look at this scenario for me. So those here can look at it. Those here, this group, you can turn and then you look at it from that perspective. Then people can join them as one group. Okay, let's try it. Let's try it. Let's try it. In a small town of Akwadum, families depend on 2 boreholes and a nearby stream for their daily water. During the rainy season, the stream often got flat and the water turns muddy, right? So you can even equate it to galamsey, anyhow you want to see it. A few weeks later, several children in the community fall ill with stomach pains and fever. Local health and volunteers support water contamination, but confirming it is difficult. The nearest testing laboratory is 45 kilometers away. Transporting the samples takes days. By the time the results comes, the people may already be sick. The community wants a simple local way to know whether or when the water is safe when the water is safe or unsafe, right? They can't afford expensive equipment, and many households don't have smartphone or constant electricity. Your role. Your challenge is to think conceptually, right? How might the community detect early signs of contamination using simple signal or tools? How could they share alerts quickly to prevent others from drinking unsafe water? And then what will be the system trustworthy, low cost, and easy to maintain, right? What will make the system trustworthy, low cost, and easy to maintain? Yes. Brainstorm around that. Look at the system thinking approach, and let's see what you come out with. Yes, the same thing. Yeah, the 2 of you can join them. Let's try it. You can come and join this group, any of this group, 1-1. Let's do it in 5 minutes, right? In 5 minutes. Now, what will be the purpose? Yes. What will be the purpose? Yes, who knows the purpose? Yes. Repeat that. without the use of electricity. Okay? Yes. Or I should give you 5 minutes or 2 minutes, yes? 2 minutes, think about it, and then let's look at the purpose. Right? Yes. How do we address this? What will be the purpose? Yes. So what are some of the constraints? What are some of the constraints? Let's identify all the constraints. One. Sorry? Is it a constraint? Yes. Low cost. Yes. Yeah. What? Constraints. Low cost. Yes. No. What are the system constraints? There's already constraints in the problem scenario, right? You have the problem, but they have given you other constraints, right? So you said low cost. Is it a constraint? Yes. Difficulty in communication. So there's communication issue. There's a low cost issue. Sorry. Electricity. All right. Electricity. They have transportation issue. Yes. This group. No, that is what led to those constraints. So what? Yes. What are the other constraints? Yes. Okay. So propose solution. What is the purpose? So looking at low cost, electricity, transportation, communication barrier, what is the purpose? Yes.
We have to think of something that does not require maybe a lot of communication. So maybe a system where it's color coded so that one you don't need a lot of communication. And we need something that can easily be made and will not be too costly.
Okay. Yes, that's a good idea. Yes. This group, you're not saying anything. Yes, say something. So she said affordable. So what will be the title? Let's say the concept, that's the project title. Let's pick the project title from the problem scenario. At least summarize it in the project title. So what's the project title? Design of whatever. Continue. Design of affordable, accessible. Okay. Yes. Yes. Any other? It says designing of affordable, accessible method for detecting water contamination. Yes, this group. What should be the title? Because you should be able to deduce that from the problem scenario. Yes. Affordable and efficient method of detecting feasible. Okay. Yes. Hello. Uh-huh. I think it's too long. Just make it simple. Something that, okay, when I buy this, the first one was contactless temperature sensor or something. Right? So this one will be, so you are selling now. So you are telling them that there is an existing one that is more expensive. So come and buy mine because mine is low cost. Yes. So you are using that one to drive as a hook, right? So you are using the low cost. Psychologically, when it says the 10% discount, you want to rush to that. But sometimes there's no discount, right? Yes. Affordable and portable. It's the same as low cost. Water what? What? Okay, so there's a low cost water tester. Yeah, yes. Any other one? Let's define it well. Yes. He's mentioned low cost water tester. Yes. Okay, come out with your input. Don't dwell on this. Use your own input. This one is for the old one. Yes. What will be your input? Okay, the title, yes. Mm-hmm.
Okay, so I was thinking that design
Mm-hmm.
simple and affordable method. Okay, solar powered design a simple, affordable solar powered to solve the issue of constant electricity. And no, that part I think is
Okay, just think about it this way. All right. Now, what do you envisage? Now, looking at the problem and what you want to address, how would the final work like the product look like? Right? Do you want to have a cup and then you fetch, let's say you have a water bottle, right? And then under it, you have the sensor. So when you pour the water, it detects and it gives you a reading and tell you whether it is safe or unsafe. This one you can do a mock-up without actually designing the actual system, right? So you have this, you can have the sensor below it, or it goes through the sensor. So as you are pouring the water, it's going through it, and then when you are done, then it tells you there's a calibration or whatever, a notification on it that tells you it is safe to drink or it's unsafe to drink. But that's a different mock-up, how you want it to look like. But what will be the input? What are the things you are looking out for? In your input, yes. How do you determine whether the water is safe or unsafe? Yes. You need a sample of the water, so that's the first thing, yes. How do you determine whether the water is safe or unsafe? Yes. System thinking. Yes. How do you determine that? Yes. Are you going to look at the color yourself? Are you going to just look at the color to say that it is contaminated or it's not contaminated? Yes. But you know you can have turbidity, but you may have bad pH, right? Yeah, so it means that in your input, there are certain things you need to look out for. So mention all, that's where you need to think about, right? You need to check your what? Your turbidity, you need to check your pH, yes. You need to check your color. What happens? What is the difference between the turbidity? Yes. Sorry? Yes. So all these things will come into your input. Right? All these ones will come into your input. All the phenomenon that you are mentioning, right? Your pH level, how do you determine the pH of the water? How do you determine the turbidity level of the water, right? All this will come to that level. Yes. Right? What else? Yes, so she's saying that you need to also measure smell. It may be crystal, right? You may have a clean water, but it has a bad smell. That's what she's saying. because of that too, you don't want to drink it, right? Yes, what else? Or if you take your water bottle, I think there are certain parameters that they give you. Sorry? Yes, some they write everything on it. So this one, they tell us that the pH is 7.0 to 8.0. Right? Okay, so now you know the problem, you come out with the purpose or the title, right? Then you now go to your input parameters. So somebody says you should check the color, you should check pH, you should check the scent, you should check other parameters. You must put all of them as your input, right? And then what will be the process of determining the pH level, the turbidity, and all of that? That will go under your what? Process. Yes. Uh-huh. Yes. Yes. Your process. Yes. In logic, right? You must have the data, right? You must look into literature and have a data on safe water, right? What are the qualities of a safe drinking water? What are the parameters you need to check? So if you can Google it and check, then those serves as your benchmarking in your process. So you have all of them, right? So if you know that, okay, pH is supposed to be 7.0, okay, that is your benchmark. So that means you are going to test this against that, right? Turbidity level should be this. So this is your benchmark. So you need to check that, right? If there are certain minerals in the water, what type of minerals is acceptable and what other ones are not acceptable. So if you see potassium, nitrite, and all that in the water, you don't flag it, but you say, okay, these are accepted. But if you are seeing lead and other things, right, then you see that there's a problem. Okay, so in your process, in your input, you have it, and then the if, right? The if, which is the logic, right? The if this is this should happen. If this is that, this should happen. If this and that is seen, this should happen, right? That goes under your process. Then your output is more of your display. So when you see this, what does it mean? When you see that, what does it mean? That means after you've done the comparison, right, and you see this results, what does it mean? Well, how do you want the system to interpret it? That will come into your output. Right? Now, in your design, in the scenario, it says that there is no electricity. So in your power supply, you should be thinking about what power supply am I going to use? Are you going to dwell on AC? It means that if there is no electricity, you shouldn't be thinking about plugging anything. Do you get it? If they are in the scenario, they said they have challenges with electricity. So don't be thinking about plug, right? AC or whatever. Now it says there is a problem with communication. So what does that mean? Yes, there's a challenge with communication, and then they have a transportation issue. So because they have the lab to do the analysis is at a distance, it means that everything has to be done local. Right? Everything has to be done. So whatever system you are building, it should be, the system should be able to do the analysis for you at the same place without transporting it. Do you get it? So you must think of localizing your solution. Right? Now, because of the economic background of the people living in that particular area, okay, so you should also be thinking about their cost, right? How much is affordable? Are you going to do it 500 cities? Can they afford 500 cities? Are you going to build a system where everybody will have it at home? At what cost? Or you want it to be at a particular location, right? So you need to think about it. Whether it becomes, let's say you spend $1,000, and then you build a system, and then the water goes through that system and everybody fetch it at the end. That means that it's one-time cost, but then the operation and everything is shared among the people, or somebody sponsors it. That is one approach you may be thinking about it. Or is it less expensive to a point where everybody can own one of your device? And what does it mean to you if everybody is getting your device? What does it mean to you? Is it good? Is it going to help your impact metrics? Or you are more interested in, oh, we have one here and it's serving like 2 million people at the same time. Now, frequency of use, what will be the effect on it? What are your constraints? Your reliability, right? So you need to do what you call benchmarking analysis, right? But that's also another thing you need to look at. Any question? Okay, so that was that example. Now so that's the system thinking approach. Now let's look at another non-invasive patient monitoring system. Okay, this is rapid prototyping without going through the system thinking. Or if you've done the system thinking, then you can apply this. Then it becomes so easy, right? So if you have a solution like this, okay, now, why do you need non-invasive monitoring? It reduces infection risk and improves patient comfort, similar to the first project, right? That's also, you understand. So the moment you are reducing the contact, you are reducing contact, it means that you are improving that, right? So you are improving, you reduce the risk, okay? And then you give people more comfort of utilizing your design. Prof is working on another project where he's working with students to use their mobile phone. Mark, you would like to talk to them about the mobile phone project?
So,
If maybe some of them may be interested to collaborate.
so you want me to relate it to this? So, certainly one of the first things to think about, what are the ways to non-invasively monitor people? One is, he's talked to you about how to measure temperature non-invasively. But what else can you do non-invasively? You can do blood pressure non-invasively. So there's automated blood pressure systems. They're simple to make, really, or you can buy cheap ones. What else can you do non-invasively? You can look at heart rate. You can listen to heart. I have.
So you see, project ideas.
Yeah.
More project ideas for you now.
Yeah, these are all non-invasive things that we do. So so one of the things that actually I have students working on right now is, so the leading cause of death in Ghana is cardiovascular disease. So if you can get a non-invasive way, not only to collect heart sounds, that's not hard. We can make cheap stethoscopes with just a microphone and some 3D printing. And just like we do Android, Arduino thing, there's a rapid development system for Android. So you can turn your phone into something that collects heart sounds, and even though you have no experts in your village, you can transmit them to, some expert in Accra. So, and then you can do the same thing with non-invasive. My watch will tell me ECG, and I can tell you how to build for less than $10 a way to record ECG and transmit it remotely. So, I mean, I can build you a whole little clinic with simple, low-cost things, but the real kicker is to make it telemedicine. So this isn't, I mean, I've been thinking about this for a long time, so.
Yeah.
And
So
to me, in Ghana, because you have so few physicians per population, what you really need is telemedicine. And as bioengineers, you have all the tools to do this. You just got to think of a way to, like he says, turn it into an organization. What are the steps you need to take? Then, you know, if you want to know this technical details of how to do it, he can tell you, I can tell you, you know. But what you have to do is come up with the big thing to that. I even yell at the people who run this group today. I say, you can talk all you want about making things, but so this is an idea. It's a good idea. But how do we go from idea to making this happen so that, you know, almost every village in Ghana can have telemedicine? So I'm going way off topic now.
all right. So you can see, thank you, Mark. So you can see that there's a green area on top area. So imagine you people come together as a startup and be building non-invasive product. Right? Your startup is to build, is focused on telemedicine and designing non-invasive products to support healthcare in Ghana. That's a huge market. Right? So if it's temperature, non-invasive, blood pressure, non-invasive. Right? Even if you want to measure your pulse, non-invasive, that kind of thing. And it can be less. The most important thing is to understand how the existing system works. Because most of the time, the expensive medical device is also built because of litigation, right? Maybe if you said this is to measure temperature, and then they use it, and then someone is diagnosed wrongly, and then it leads to death or something, right? Then the doctor says, it's not my fault, it's because of the device. Who built the device? Then you need to go and see the manufacturer, and then they sue you, right? So in order to do that, then you need to put a lot of complexities in place to safeguard the manufacturer, right, or the company, so that when something happens, it is not their fault. In doing that, you increase the complexity of your design, and then what happens? It becomes more expensive. But the actual thing you want to do is to check the body temperature. So to check the body temperature is your microcontroller, your sensor, your power supply. You are done. you see that. But when you go into it, you see a lot of different circuits, a very complex circuit, because you want to make sure that all the things, that the possibilities, all the scenarios are built into it, such that if it happens, then it is not you, the manufacturer, but it's the lab technician or the nurse. It's not your fault. So then it becomes more expensive, right? But your startup can be addressing the basic needs of the people. Do you get it? Imagine a pregnant woman goes to the hospital, sit down for 2-3 hours, just for the doctor to tell you that, oh, it's just a normal pregnancy symptoms, so go back home. Right? So if those samples could have been taken, right, and transferred, because now everybody, your phone is closer to you than anything, right, and transfer it to your doctor, right, and then your doctor interprets it and tells you, oh, there's nothing, you need to take rest, you need to drink water, you need to take a walk or something. It saves you from walking all the way or driving all the way. And when you are driving to the hospital, you are increasing emission. Right? You are increasing emission, and then you're contributing to global warming. So you see how your simple thing cascade into other things. So in your design thinking approach, you should have empathize. That means identify the patient's safety needs, define or frame the challenge, and then you do the ideation, which is the brainstorming solution using the sensors, and then you do your prototype, you test to validate, and so on. So you say that rapid prototyping is equal to quick iteration plus hands-on learning, right? Quick iteration, right, plus hands-on learning is equal to what? Rapid prototyping. So for that project you are working on, then, so your project is a non-invasive patient monitoring system, right? Your system review or system component, what do you need? Every system will need a power supply, right? But as to what will be the power requirement, you have to look at it. Where am I going to use it? What will be the total load and demand? So what type of power supply? Is it a 5-volt power supply? Is it 12-volt power supply? Is it going to be a range, 5 to 10-volt power supply? You have to look at the power supply. Now, is it an SMD you are going to build, right? Or are you going to use a battery powered? You have to think about it. Each one comes at a cost, but you need do your cost analysis, you figure it out. Now, which microcontroller should I use, right? If you are looking at low cost, are you going to just buy the microcontroller without buying the full Arduino? Because the Arduino board is a test board. You don't need to put it in a project. It increases the cost of your project, your product, right? It's a test board. This is a test board, right? But you find students putting this in their project work. All you need is the microcontroller, right? And then you build you condition it with your crystal, your reset button and everything. Then you tap your IOs and use it for your project. So you don't need to put the whole of this and then load the firmware. You don't need to put the whole of this in a project and submit. But people don't know, so they do it. And it's too expensive. You need to always keep this for your testing and so on. All right. So the next thing will be based on your input and your system flow and your logic flow, you should be able to come out with your block diagram, right? We use the IPO model, which is your input, process, and output, right? So in your input, what are the parameters you are looking at from your input, right? So you want to sense the temperature, you want to do to give an alert, and then you want to do so you have the buzzer that gives you the alert, right? The sound. So it gives you that, oh, okay, it's beeping or something. Then if you are thinking about telemedicine, right? So you do it here, you want the doctor in Navrongo to have a notification. Then you are thinking about IoT. Okay, so simple project, you scale it. So you do it local and now you say you want to transfer it. So if you want to do that, which of the medium do you use? Do you use ZigBee? Do you use radio frequency RF? Do you want to use a Wi-Fi? What medium do you want to use? Depending on the distance. Each one comes at a cost. So it's also factored in your R&D, right? Then when you are done with your block diagram, so you do your block diagram before you do your wiring, right? Now when it comes to your wiring diagram, there are so many softwares, okay? So for rapid prototyping, you can decide to use Tinkercad, you can use Fritzing, you can go further to say you are using Fusion. Fusion 360 now has both the circuit portion and the 3D modeling portion. You can look at it from that perspective. You can use Mortison. You can decide to use Proteus. There's so many software. You can use, there are a lot, depending. If you want to, for rapid prototyping, you like Fritzing, Tinkercad, and so on, it's easy. But if you want to move it a bit further with your project by designing a custom PCB, right? Then you need to also look at your level, okay? With your level, with Fritzing, you can make a simple PCB with Fritzing, right? How many of you know about Fritzing? Oh, so I'm mentioning something you don't know. Sorry. So let me show you this. That will be done soon. Here. So this website, this prison, right? You can have this offline. You can have this installed on your computer. It's similar to Tinkercad. Nowadays, you can even write the code and simulate it, right? You can write the code and simulate it. You can go to download, right? It's similar. So you can also have the Arduino plugin, add all the components. It's for rapid prototyping. So you can use Fidzin. You can also use your normal Tinkercad. So this is your normal Tinkercad. Here you can write the code, right? So you come here, you go to create, then you go to circuit. Okay, right? And you pick your Arduino board, and then you pick your breadboard, you connect your component to it, depending on what you want to do. You want to power this from ground, so you connect this, depending on what you want to do. You got this to this, you change the color to black, you take your 5 volts, you come here, you plug it, you go there, you change the color to red, okay? And you've powered this, you get your LED here, you get your resistor over there, then you connect this to red, then you connect this to black, you change the color, so you can change this to black, and then you simulate it. Perfect. You test your idea, finished, within the shortest time. All right? Within the shortest time. So that's why you call it rapid prototyping, right? If you want to write a logic to control the flow, right, then you don't need the 5 volt here anymore. You don't need this anymore. So I connect this. I can go all the way to this side. I can connect it to pin 13, something like this. I'll rent this very well. And then I can click here and make it look good. Okay, and change this to maybe green, right? So I differentiate that. And then I come to code, all right? You can use blocks to code it, depending on your level, and then I can simulate it. And then I'm blinking the LED, right? So the code says forever, built in. If it's low, turn it red, on, off. You're done. Hello. So that's rapid prototyping. You get it on the breadboard, and you get a lot of these things done. Right? Then you can also convert this. You say you want to see the test. You don't want the blocks. You want to see the test. So this is the test. Okay? So the same code. Right? So you have the test there. You use C++, and then you can code it, and you have it running. You can add your LCD. You can add your sensors and build from the basic thing to that. So right from sketches to your breadboard, to your simulator, to your breadboard. Then from your that, you move on to more advanced software like Fusion 360, like Multisim, like Proteus. Then you are building and you move on. Maybe in the next workshop, we'll be looking at custom PCB design. Okay, so same project, you move on from custom PCB design, and you can build something like this. So easy, right? All right, so now when you are done with this, I think I'm left with some 2 slides, I'm be done. And you take your questions. If not, close. Right? So when you are done with your system block diagram, your system wiring diagram, then this is the flow chart. This flow chart will allow you to write your code. Right? You have hardware consideration and you have software consideration. Under the hardware consideration, we are looking at the block diagram and then the wiring diagram, right? Under the software consideration, we are looking at your flow chart, your pseudocode, your flow chart, anyhow you want to look at it. Then based on this, you write your code, right? So first you initialize. Then the temperature, the sensor will measure the temperature, will read the temperature. Now, you say that if the temperature is low, what do you do? If the temperature is high, what do you do? Right? So you use, based on your flow chart, then you can write a good programming, a good program, right? Then when you are done, you look at your risk mitigation. That's something you can do. Then you can, after you are done, you can do assembling, right? After you are done, you load the code. So that means you build everything on the breadboard, you load your sketches, then you test the variance, and then you debug among your team, and then you do room temperature. So if the temperature is around this, 28 degrees Celsius, no alert. If the temperature is above this, you put on the buzzer. If the room is cold within this, you turn off the buzzer, right? Something like that. So, and then design control, you look at your design flow, evidence-driven engineering cycle, requirement, validation, verification, and validation. So you take the requirement, you do the validation, then you do verification. So under the requirement, design, verify, okay, then you validate, you do the risk review, and then you release. Now, how can this system be improved? What other vital signs could you measure using non-invasive approach, right? And then how can data be stored or transmitted securely? So based on now that you have the data, you are looking at the next level. So you see that simple project becomes very complex. And then if you have a business mindset, then you are building a startup around it, and then you commercialize it. All right, so these are all parts of it. All right, rapid prototyping isn't the end, it's the beginning of understanding. Innovation in biomedical design begins with curiosity, teamwork, and the courage to build. Thank you so much for your time. Yes, one question, and then we are off from here. What's high for you? What did you pick up from this workshop? Yes. What's your takeaway? Who can say it? What's your takeaway from this workshop? Yes. Okay, yes. Yes. Yeah, that's labor, right? Okay, so when people take ChatGPT and then they said, oh, don't you use it, do you use it? So there's a lot of discussion. Students should not use it, students should use it, students should use it with guardrails and all of that. For me, don't outsource the thinking. Don't outsource your thinking, but you can outsource the labor. Right? Don't outsource your thinking. Let the machine do the labor, right? But the thinking should be done by you. You know what you want. You know all the parameters. But when it comes to the labor side, you can outsource it to a machine to do it. Do you get it? That's why in every system, they look at the repeated tasks or activities. It says, for this, okay, let's automate it. Right? Because if not, then you need to hire a lot of people to do the same thing. So if I have to do data analysis, right, I need to go get a lot of people to do that. That one I can outsource it to a machine to do that for me. But how I collect the data and how the means of collecting the data and everything should be done by you because you know what data you are collecting, right? And what information is more important to you and which one is not before you even outsource that. All right. Thank you so much for the opportunity to have this workshop with you again. So this is our second workshop together. The first one was at University of Ghana. And
A little while ago.
yeah. All right. Anyone interested in internship who want to collaborate on capstone projects with other universities? Not. You can talk to me later. All right. Thank you, Mark.